Okay, so I rearranged the presentation so that we go according to the order. So first, as I said, we need to understand the composition of rotations to get an equivalent. Then we go back and solve this example, and then we go to similarity transform. But first, composition of rotations. Well, there are two ways that you can do the composition of the rotations. One is the rotations that you are composing, or not combining really, they are all done with respect to a current frame axis. What do I mean? So let's say here, I first rotated my initial frame of knots, frame 0, with an angle phi about the y-axis. And the intermediate frame, I call it x1, y1, and z1. Now, in order to go from frame 1 to frame 2, now I can do two different ways. And let's say the rotation I want to do is the z-axis. So what I want to do is first a y-axis rotation followed by what? A z-axis rotation. In the beginning, the inertial y and the moving y, y0 and y1, they are on the top of each other. So the first rotation you do phi can be described along any of them. This phi can be said about y0 or y1, fine. But now that you have two different frames, now you see the axes are different, z0 and z1 are different. Now when you say followed by a rotation of theta degrees along the z-axis, what z are you talking about? Are you talking about the intermediate z? We call it the current z also, z1. Or you still want to rotate this frame 1, all of its axes, by rotating all of them about what? About the original z, z0. In most of the applications in real life, the rotations are done about the current or the intermediate frame. So we call those rotations, we call them intrinsic rotations. Okay, so if the angle is described with respect to one of the axes of the moving current rotating frame, we call those intrinsic rotations. Sometimes that's not the case. As I said here, I have rotated first an angle of phi about y-axis, but now instead of me rotating frames x1, y1, z1 about z1, no, I'm not going to keep z1 fixed. Everything is going to rotate angle theta about z0. So what's the result of that? The result of that is going to be that if you can see here, your z2 is not going to be the same as z1, your x2 is not going to be the same as x1, your y2 is not going to be the same as y1. All three of them will change because none of them will coincide with z0. So all of the three x1, y1, z1 will change to something new for x2, y2, z2. In this case, no. Since I'm rotating about z1, z1 and z2 are the same. The final z and the intermediate z are the same. It's just x2 and y2 that have changed. But here, everything does change. Okay, so whether I'm doing my rotation about the original or the fixed frame, or I'm doing it about the current frame, that changes the way we combine the rotations into one single equivalent. Now, if they are intrinsic current frame, how do you combine? Well, I just showed you above here that if you know the coordinates of a point in one frame, correct? Where was it? You find it here. If I know the coordinate of point in one frame, I can find it in the other one by pre-multiplying by a rotation matrix, multiplying from the left. So the case is here. Let's say I have one single point P. Okay, I have one single point P here. And the coordinate of this P, I can write along x0, y0, z0, or x1, y1, z1, or x2, y2, z2. So I can find the coordinate of this along any of those three sets of frames, and I would call them what? I would call them P naught. I would call them P naught. I will call them P1, and I will call them what? P2. Good. So what I can do is this. If I multiply coordinate of P in frame 1 by the rotation matrix of R of 1 with respect to 0, I get P in 0. If I multiply the coordinate of P in frame 2 by the rotation of 2 with respect to 1, I can go to what? Frame 1, P of 1. Now my question is this. These are the two rotations I have done. I first gone with this from 0 to 1, and then with this one, I went from 1 to what? 2, correct? So these are the two rotation matrices that I have used. So from here to here, what I did was, or actually if I want to go back, that's correct, is this way. If I want to, I have something here, want to go describe it back here, I need to use R10. If I have something in 2, want to go back to 1, I have to use R21. So the question is, if I have something in 2, can I directly go to frame 0 by one single rotation matrix? And I would call that rotation matrix 2 with respect to 0. Okay, I want to replace those two with one equivalent rotation. The question is, what relation does this guy have with those two? And it's not really hard to show that. If I combine these, the result should be pre-multiplication. Why is it? Because if you replace from here, you see that P naught can be written as what? Let's just combine the first two. P naught is R10 times P1, but P1 itself is R21 P2. So it is R10 times R21 P2. So you can write it as R10 R21 times P2, correct? So that's what you get. And now compare that against this last one. If you see, it means that clearly your R20 should be the same as what? R10 times R21, and that's what you see in this box. Okay, that's the important thing. If the rotations are about the current frame, how do I go from the first frame to the last, or basically from the last frame to the first, any of that? All I need is to go according to the order. Which rotation happened first? R10 happened first. So I first put that on the left. Which rotation happens next? 2 with respect to 1. This was next, so it's like first come, first served. If you were the first rotation, I put you on the left. If you were the second rotation, I put you second on the left. The last one will go on the right. So this is what we call, this guy here is what we call pre-multiplication. So we pre-multiply from the first one to the last one, and that means combining them all together. Okay, so this is about intrinsic rotations. Okay, so here I added it for you, and I wrote it clearly and nicely for you, that we call this pre-multiplication. The other way, as I said, to combine is to rotate in each step with respect to the initial frames, with respect to the fixed frame. We call it extrinsic rotation. Now, in this case, if I can go back from frame 1 to frame 0 by R10, and then I can go back from frame 2 to 1 by a rotation matrix called R. Now you might say, why didn't you call it R21? I'll tell you why. But if I can do that, then if I want to go with one step from 2 to 0, and I call this R of 2 with respect to 0, the way you do it is backwards. You first put the last matrix, the last rotation, then the first rotation, the second and the first. The order is reversed. Or if you want to say you start from the beginning, the first matrix, you put it on the right and then go to the left. You go from right to left and multiply from first one to last one. Here you went from left to right when you go from first one to last one. So this is called pre or left multiplication. This is called post or right multiplication. Okay, now why is that? So let's talk about why the order will be reversed. Well, the reason is, the proof of that is, for that I really need this similarity transform. So that's quite interesting that you really need to know some stuff before you can delve into much more of the explanation. So let's talk about the similarity transform right now. What's the meaning of this? Let's talk about it, and because here in this bracket I have done a similarity transform. What is that? So far I have learned something. I have learned that if I know a point P or any vector, let's not just say P, any vector like F or whatever, if I have this guy written in frame 1, and now I want to write it in frame what? 0. All I need is to multiply it by R of 1 with respect to 0. So I know how to transform a vector from one frame to another. Now the question is this. So let's say this is an n by 1 vector. Correct? And it's not really n by 1, it's 3 by 1. That's all you can do. Right? Because you know this guy is a 3 by 3. So this has to be a 3 by 1 and this has to be a 3 by 1. Good. Now, the question is this. What if you have a matrix in frame 1, like A, right? What if you have a matrix in frame 1, A, and now you want to show it in frame what? In frame 0. So A is in frame 1 and B is in frame 0. Correct? So this guy is written in frame 0, this guy is written in frame 1. And this matrix, okay, this has to be a 3 by 3 actually. So I'm going to transform a matrix 3 by 3 from one frame to another. Can you transfer or transform matrices as well? The answer is yes, you can. Yes, you can. How? So the way to transfer that is following this transformation here, this equation. What you really need is to, from the left side, multiply it by inverse of R of 1 to 0. Okay, so if it was a vector, you simply multiplied it by R of 1, 0, but not anymore. Okay, so you not even multiplying it by R of 1, 0 directly, you're multiplying it by inverse of that from the left and then from the right by R of 1, 0. Okay, as you clearly can see in this formula. And since everything here is a 3 by 3, you're not going to have any problem. Okay, everything is a 3 by 3. So the transformation can be done. And we call this a similarity transformation. So what's the meaning of similarity transformation? Where would you use it in real life? When is it that a matrix is written in one frame and you want it in another frame? So let's talk about it. Why do we call it similarity transform? As I said, I have to talk about it first. So let me talk about it and then I come back and explain what happens to this backward multiplication here. Okay, so why, first of all, what's the application of it? Where would you use it? I mean, for vectors, I could understand, right? You could transfer a position or an angular velocity or a vector. That's quite easily understandable. But matrix, what about the matrix? And the answer is yes, actually, there are so many places that we do transform our matrices from one frame to the other. And you might say where, and I tell you, for example, in statics or solid mechanics. If you remember when we had, let me see if I can get a nice picture from here. Maybe this one. So here I have this object, wrong selection. So here I have this object, and from what you know in statics, I ask you to find the moments of inertia. I ask you to find the moments of inertia of this rigid body in frame cap XYZ. So I say, for example, what is IXX? What is I cap XY? What is IZZ? And so on. You know, there are 9 components in the I matrix, in the moment of inertia matrix, and I'm asking you, what are those? Well, the thing is here, your rigid body is so much rotated with respect to the original frame cap XYZ, has rotated 3 angles, that if you want to calculate these guys by those integrals, that's not easy, right? For example, if you remember, IXX was what? It was the integral of y squared plus z squared, correct? The whole thing dm, and the integral is taken over the mass of the part, right? And similar thing for x, y, z, z, and so on. Just refer back to your statics. Good? But again, basically the decomposition of the part, or the situation, the orientation of the part with respect to cap XYZ is not something trivial. There are so many angles involved, and that's not easy to calculate. But instead, if I ask you, hey, what is I about the small x's z? Well, that's not hard, because the small x, small y, and small z are such that they are always attached to the rigid body. They are not affected by any of these rotations. They are body attached. And first of all, they are easier to calculate. Why? Because, for example, for this object here, z is the axis of symmetry. And so I can easily calculate it by a single integration instead of, you know, these integrations are actually what? You know, these integrations are triple integrations, right? So instead, I can do it with a single integration with respect to one angle. Here, for example, phi, although that phi is not necessarily the phi I want to integrate with, but this integration is way easier. And then, for example, xx and yy, because again, this object has axes of symmetry, I know that I small xx is the same as I small yy. And because, again, of that symmetry, all of the product terms, IXY is the same as IXZ, and it's the same as IYZ. They are all 0. Okay, so your inertia matrix, I, as written in the small frame XYZ, is something like IXX, IXX again, because as I said, Y and X are the same, IZZ, and then 3 zeros here and 3 zeros there. So the inertia matrix in the small frame, the body attached frame, is very simple, extremely simple, right? But if I ask you, what about the cap frame? Well, that's not that easy. Because about the capital frame here, definitely, first of all, none of those axes is an axis of symmetry, cap XYZ. Second of all, as this object keeps rotating, the orientation of the rigid body with respect to the cap XYZ would change. So those guys will not be constant. They will have time derivative. Okay, not only you are going to have 9 components, so your I cap XYZ, is going to have 9 components. Not only that, actually they are not even going to be constant, because as the object rotates, the orientation of the object with respect to cap xyz does change. Okay? So here I can say that this guy and this one, the only 2 numbers I need, they are constant numbers. But here, no element is constant with respect to time. And so you might say, okay, what's the importance? Well, the importance is this. When you go in dynamics and you have the equation that sum of the moments, let's say about the centroid, is equal to d over dt of h about the centroid, the angular momentum. And if you remember, the angular momentum is I times omega, right? The inertia matrix times angular velocity. When here you're taking time derivative, that's the hard part. Here is a product, and if I has variable components, it has to be di over dt times omega plus I times the omega over dt. And while this one is related to alpha components, and depending on what frame you're using, like a cross product, just go and look at that video, like cap omega, small omega, but this one is not going to be even easier to calculate. Okay, it's not easy. Why? Because it depends on how you are writing this. Now let's talk about that important thing. So this is my equation, right? Now when you write this equation, before even you take derivative, the important thing is this. Let me put it back, that's okay. The important thing is this. You see, this is an equation that is always valid, okay? This equation, angular momentum, is always valid. Now the question is this. When you write this equation, something like sum of the forces equal ma, correct? You know this equation, we use it over and over in kinetics of rigid bodies or particles. And this equation for a particle or a rigid body with a constant mass, it's always correct regardless of what axis you are writing it. So you can write it along the x-axis, you will get this one. You can write it along the y-axis, you will get this one. You can write it along, so let's say this is a small x or capital X, this is a small y. You can write it along, let's say, capital Z. You can write it along small x, and so on and so forth. So as you can see, I can write that equation along any axis that I want, whether inertial or not. It does not matter how I'm decomposing it. It does matter that when I calculated A, it is calculated with respect to the inertial frame. Okay, but how then I decompose and write it as a combination of which unit vectors, that's up to me. So here we have 2 different things, and that's where I want to focus on. One is how you measure something. The other one is how you write something. Okay? So the thing that we have here, and that is very important, is measurement versus writing or decomposition. I can measure, my sensors are such that they measure, or my calculations are such that they should measure my acceleration always with respect to an inertial frame. Otherwise, my Newton equations are not valid. Okay? But now that I found this free vector A, this free vector A and this free vector F, because they are free vectors, now I can write them, their magnitudes, whatever their magnitude is, it's just a free vector in the space. I can now decompose it along any coordinate frame that I desire. Okay? Because I have done my measurements, I know the value of this free vector, now I can write it in any direction. And the important thing is now this. When you have an equation like this, which is always valid, and you're writing it along a coordinate frame, everything in that equation should be written along the same axis. So when I'm doing this moment, if I'm writing this moment about the small frame x, y, z small, then the I should also be what? About I, it should be written along small x, y, z, and omega should also be written about what? Small x, y, z. Okay, so you cannot, for example, say no. I want to write my I and M about small xyz, but I want to write my omega about cap xyz. You cannot do that. Everything in an equation, when you're doing arithmetic, multiplication, division, addition, subtraction, everything has to be written along one set of frame, right? Here you cannot say, I want to say sum of the forces along capital Y axis is equal to m times a about the small x axis. Of course you cannot say that. The same thing here. These physical entities, m, I, omega, everything has to be written along the same frame. So now, if instead of small xyz, I go with capital XYZ, what happens? If I write all of the components in this equation about cap XYZ, what can happen? Well, guess what? Here, the components, as I said, the components of the cap XYZ these guys, none of them is time constant. So this term is not zero. It's equal to a 3 by 3 matrix, and nothing here in general could be equal to 0. Okay? And that makes calculation of this a lot harder. Why? Because this I, each entry in it, each one of those 3 entries in general could be a function of what? Phi, theta, and psi. And now there are going to be lots of sine and cosines in each component, and now you have to take time derivative of them and use chain rule. And this is going to be a very, very scary looking equation. So it's always good if you have an inertia matrix that you calculate the components of that inertia matrix with respect to what kind of frame? You're right, a body attached frame. It's not a good idea to calculate the components of an inertia matrix with respect to what? Inertial frame. Absolutely not a good idea, because then the components will have time derivatives. Okay? So now I can use the similarity transform, and I say, hey, if I call 1 to be what? My, let's say cap XYZ. And if I call 0 to be my small xyz, based on this one, correct? Based on this one, this A, correct? This A, you know here, A is written in what frame? A, if you remember, A was written in frame 1, B was written in frame 0. So here again, I call my 1 the cap frame, and A and B, I want both of them to refer to what? To the inertia matrix. So my question is this: if I have I of the if I want I in the body attached frame, how do I find it? Well, it says all you need is to multiply R10 inverse times I in the inertial frame and multiply it by what? R10. Okay, so if you have this one, you can get this. If on the other hand, most of the time you have this one, You want this, you can do the opposite of that, right? So if somebody says, what is your inertia matrix in the capital frame? Because in the small frame, I could do those integrals and find them. What is this one? All you need is to apply the inverse. So you can do the inverse of that as well. And if you want that, then you can show that the I of cap xyz is equal to R10 times I small xyz times R10 inverse. Or since you are going from frame 0 to 1 in that transformation, instead, you can also write this as what? R01 inverse times I small xyz times R01. Right? So if I know this guy through integrations, and if I ask you to give it to me in another frame, like the inertial frame, you can easily do it. So yes, this similarity transformation have applications. You can go from one frame to another and transform something like the I matrix. What else can you transform? The sigma matrix, the stress matrix. If you remember, sigma, let's say xx, correct? If you remember, tau xy and tau xz, as well as tau yx, sigma yy, and tau yz, and similarly tau zy, tau zx, and sigma z. So you can also transform your stress matrix from one frame to the other, and you can also do what? You can transform your strain, right? Epsilon xx, correct? Gamma xy, gamma xz, and then gamma yx, epsilon yy, gamma yz, and then gamma zy, gamma zx, gamma zy, and gamma epsilon zz. Okay, so these are the three important matrices in engineering for us: stress, strain, and I, inertia matrix, that sometimes we have in one frame and we want to transform them into another frame, right? Because describing it in one frame is way easier than the other one. So in one frame we can easily get them. In the other frame, we can just do the similarity transform to get them. And one of the major places that we use this, if you remember, were the principal axes. I don't know if you remember them or not, but one of the places in the statics that we talked about is the principal axis. So you have an arbitrary I matrix, correct? And I guess I made a mistake here. So you had your I matrix, which you calculated with respect to one set of frames. And then these product terms were not in general zero. Correct? So these guys are like not zero. And you know, this is a symmetric matrix, so the yx is the same as xy, xz, and yz is the same as zy. Then you could transform this into a set of new frames, which are the rotated version of the original ones. And in this frame, if you call it prime, you had now I x prime, I y prime, I z prime, and everything else, these products, they were all zero. So these were the regular x's, these prime frames, which were acquired by rotating the xyz by, in general, 3 angles. In 2D, just 1 angle, right? In statics, we only looked at the case of 2D, so we only found 1 angle. In general, you need 3 angles. This set of x's about which no product term is existing, we call it what? The principal axis. Right? So finding the principal axis, the principal planes, the principal stresses, principal strains, and so on, all can be done using this simple formula of going from one matrix in one frame to the other. And the proof of that, if you want, I can prove it later, but I guess the video is going just too long. So I'm going to skip the proof of this, but if you want, I am going to provide the proof of this as well for you. Good. So now let's go back, see where we were. Remember, I told you when I'm combining the rotation matrices, if I'm doing it with respect to the current frame, I do pre-multiplication. I multiply from left to right, from the beginning to the last, to the end, right? From the first to the last rotation matrix. If I'm doing the rotations with respect to all of them, the axis of the fixed frame, then I have to start multiplying from right to left, from the first to the last rotation matrix. We call it post-multiplication. Why is that? The thing is this. Actually, I have two rotations here, right? R10 and R. And I said this R, I'm not going to call R of 2, 1. I just called it R. Why is that? Why didn't I call it R of 2, 1? Because this R of 2, 1 means something when the rotation is done from frame 2 to 1, right? So this guy is supposed to take you from 2 to what? To 1. But that's not the case here. Your frame 2 is not obtained by rotating about one of the axes of frame 1. If you see, my rotation is done about one of the axes of frame 0. Okay, and what did I rotate about one of the axes of frame 0? I rotated frame 1 about the axis of frame 0. So I cannot call it R20 because 20 like this means I directly go from 0 to 2. I do some rotation to 0, which directly takes me to 2, right? And I cannot call it 2 to 1 because it means I do something to frame 1, right? I rotate frame 1 about one of its axes, and it takes me to frame 2. Here, I have rotated the 3 axes of frame 1, but about one of the axes of frame 0, not one of its own axes. So not only I cannot call this 2, 1, I cannot call it 2, 0, so I just call it R. Good? Now let's go back and see why is it that I have to post-multiply. Well, this rule still applies, okay, except for this middle one, right? So what I have in this case is, if again I have a point P, the point P between 0 and 1 is clear. I can go from P in 1 to P in 0 by multiplying by R1 with respect to 0. No worries. I can also, if I want, go from what? 2 to 0 by having P in 2, go to P0 by this guy that I want to find, R20. Fine. What about this R? How can I use this R? So this R takes me from frame 2 to frame 1. So I can say that P in 1 is R times P in 2. Okay? So if I combine these 3 like last time, I can see that P in 0 can be, or if I combine, sorry, let me just go directly with R. R to 0 can be written as r times r10. And you might say, well, this is the pre-multiplication. Sorry, it has to be, my bad. It has to be r10 times r. So if you combine, it will give you something like the previous case with one caveat, with one difference. If you look, this guy, the reference of it is frame 0. This guy, the reference of it is frame 0. What about this one? Is this one, the reference of it is frame 0? The answer is no. This one has what? This one, where did you start it off? You started off frame 1. You move from 1 to 2 with this r. So this, whatever it is, the reference of it is in frame 1. Because I started with 1 and went to 2 using cap r. But remember, I told you in an equation, if we have some matrices or vectors and they are multiplied, added, anything, all of them have to be written in the same frame. I cannot have two of them start with the reference of 0, one of them with the reference of 1. It cannot be. So whatever it is, I have to take this guy and write it with reference to frame 0, not frame 1. And how can I do that? Remember, this is a matrix. And that's where I use my similarity transform. I have something in frame 1. I want to go to something in frame 0. I use this relation, right? That's the same thing. This guy, this r, that I called it r here, this one, is in frame 1. I want to take it to frame 0. How? So this is equal to what? r10 inverse times r10. This is how I take it from its reference, which is actually 1, to frame 0. And now I plug this guy into this equation. That's the right way to do it. Everything now will have reference of 0. So r20 is going to be what? r10 times what? r10 inverse times r10. And here, these two matrices would cancel because it's the matrix and it's inverse. It becomes I, not cancel, becomes I. And I times something is itself. So it is going to be rr01. And now if you look at the order, it is what? It is backwards. The second rotation is done first, then the first rotation. So it is basically like if you want to go from first one to last one, you are doing backwards. It's called post-multiplication. Okay, so hopefully I could clarify why is it that when you do extrinsic rotations or rotation with respect to fixed frame, you do backward multiplication or post-multiplication. Good? Everything clear here? If everything is clear, now let's go back to our example and finally finish this long video. So what can we do here? What was the problem in the first place? Let's review that. We've gone to so many side things and then we have to come back here, so let's review it. The problem was this. As I said on my channel, I have shown you that I rotated a rigid body from an inertial frame cap XYZ to some final body attached frame small xyz through 3 rotations, psi, theta, and phi. And here all of these rotations are with respect to z, x, and z of the current frame. So if I ask you what is the rotation matrix that can be equivalent to all 3 of these, so instead of going step by step, I want to go directly all the way back. How can I do it? you will say, well, first you did the rotation of z with angle psi, then you did the rotation of x with angle theta, and then you did the rotation of z again, current z, with angle phi. And since you did it with respect to the current frames, so you do pre-multiplication, and that will give you the resulting rotation matrix of what? Equivalent to all three Euler angles. And here, you know, this is the form of a z rotation matrix, this is an x rotation matrix, and this is another z rotation matrix. If you do that by MATLAB through symbolic toolbox, which I'm going to show you, it will give you this 3x3 rotation matrix, which has a bunch of sines and cosines. Again, the name of these angles are called precision, nutation, and spin. Good. So the rotation matrix is clear, right? Now let's go back here. What is the question? The question is this. I want you to tell me what is the angular velocity of this object that is rotating with all three theta dot, phi dot, and psi dot. What is the angular velocity of this object with respect to what? The inertial frame, right? Omega has to be with respect to inertial frame. But when I try to decompose it, when I try to write it, this omega, I'm not going to write it with respect to cap xyz. I'm not going to write it about the axis of the original frame. I'm going to write it about the axis of what? The body attached frame. I'm looking into this. Can you give me that? And here I have done it, as I said in that video, through a bunch of geometric and projections, and I showed this is the result. Okay, these components, these projections with psi dot, phi dot, theta dot, and sine, cosine of phi and theta will give you that omega. Okay, but I had to do a lot of geometry here. Now, my question is, could I do it without all of this geometry and directly using this idea of transferring one vector from one frame to another? Can I do that? And the answer is yes. How? Well, let's find out how I can do it. And here I have to add another notation for you again. So here, in order to specify my omega a little bit cleaner, I have to use 3 sub and superscripts. So the notation I'm going to use is going to be like this. Omega 101, like this. What's the meaning of that? It means the angular velocity of frame 1 measured with respect to frame 0. Okay, in this case 1 here, as I said in this example, 1 means the body attached frame, 0 means what? The inertial frame. That's what I want. The omega of the body attached with respect to inertial, measured with respect to inertial, because frame 1 is attached to the rigid body. But when you want to write it along the axis of what? Frame 1. Okay, so let me add something here. Not say with respect to measured, right? It's measured with respect to frame 0, and then when you want to write it, you write it with respect to the axis of frame 1. Okay, so that's a notation, and I'm trying to use that whenever I need something like this. So that's what I need to find. Good. Now, is that easy? Probably not too much. What's easier for me is to find this guy instead. What is this one? That's the same omega. It is the very same omega, if you look at it. That's the same omega, omega of the rigid body with respect to the inertial. The vector is the same. They are the same vector, but instead of finding it with respect to the body attached frame, it's easier, and I'll show you, it's easier for me to find it with respect to inertial first, and then go from here to here. So the vector is the same. This omega thing here is like that vector P for you. I have it in frame 0, now I want to write P in frame 1. But first, let me find P in 0. As I said, it's easier. Why is it easier? Well, let's find out. So if you look here, my first rotation with angular velocity psi dot is along the cap z. So I can easily write my first angular term as simply what? 0, 0 psi dot, because it is along z. No big deal. What about my next angular velocity? It is happening along the intermediate x. So it has a form like this, theta dot 0, 0, but remember, this theta dot 0, 0 that you have, it is in this intermediate frame which has already rotated by angle psi about the z-axis. So it is along the axis of a new frame, not the inertial frame. Okay, this vector that you have, this vector is written in the intermediate in the new frame, not in the old frame, in the cap xyz. If I want to take it from this new frame back to the old frame, because again, I'm adding, look here, what I'm doing here, I'm trying to add 3 entities together. This one, and this one. Each one of them is one of the terms of the angular velocity. This is the psi dot term, this is the theta dot term, this is the phi dot term. I'm adding 3 omegas together. Okay, I'm adding 3 omegas together. But how can I add them together? If you look, the result should be written in what frame? The result should be written in frame 0. So whatever this guy is, whatever omega it is, whatever you want to call it, it has to be written in frame 0. Whatever omega this one is, has to also write it in frame 0. Whatever omega this one is, you still had to write it in frame 0. You can only add apples to apples. You can only add stuff together that are all described in frame 0 and get the result to be in frame 0. Okay, this guy here is not omega prime in frame 0. This is omega prime in the prime frame. This is omega, this omega, which is theta dot about x-axis. This is measured with respect to x prime, not capital X or capital Y or capital Z. So when I want to go back from here to here, you know how I should do it, right? I should multiply it by the rotation matrix that can take me from here to there or from here back to there. And what did I do? I did a rotation of Z angle psi, so I need to multiply it by rotation matrix Z and angle what? Psi, and this is what you see here. This is that rotation Z and angle what? Psi that I multiplied to it. To take it from the prime frame back to the 0 frame. Finally, I have a rotation of phi dot with the z-axis about the z, but with z, intermediate z. If you look here, where is that? Phi dot here. It's the final or intermediate final z, which is basically frame 1. So there is a prime and double prime. This phi dot is about the last frame, about frame 1. But how did I go from the inertial to this frame 1? First, I did a rotation of z and psi, and then it was followed by a rotation of what? About x and theta. So if I want to go back from here to there, I have to what? Use the product of these two which is the equivalent rotation matrix, correct? So it is going to be R, Z, and psi times R of X and theta. Have to get the equivalent and then what? Multiply it to get back to this frame. And this is exactly what I'm doing here. This is what? This is like an omega, but it is written in frame 1, this omega double prime, or omega. This is like an omega 1. And here I have multiplied it by R of Z and psi times R of X and theta. So when I carry out all of these projections back to frame 0 and add them together, this is what I will get. So if somebody tells you, hey, what is the omega of the rigid body with respect to the inertial frame, and also written in the inertial frame, what is that? This is the result. This is the answer, which, as you clearly can see, is different from what we derived in that video lecture. These two are different. You can clearly see that, right? They have some similarities in general form, but the results are completely different. Okay, why is that? Because, as I said, both of them show omega of 1 with respect to 0. Both are showing the same vector. But what I have derived so far was in frame 0. What I really want is this very same vector, but in frame 1. And how can I do that? Well, the thing is, how did I go from frame first one to the last one? Okay, what I did was, if you can see, I first did a rotation of Z and psi. So if I want to go back, this is a rotation of Z and psi, as you can see here, was followed by a rotation of X and theta, and then was followed by a rotation of Z and phi. So if I want to go back from here to here, I have to multiply by the product of them, as I said. Good? Which is this matrix. Correct? But guess what? I don't want to go that way. I actually want to go backwards. I found everything with respect to this frame 0. I found this. Remember, cap Z is 0. I found this one. I want to come back here. I want it with respect to frame 1, which is a small xyz. Actually, I want to go this way. How do I go? So if this product of these three, as I said, I called it R, this R. If I want to go back, instead of multiplying by R, pre-multiplying, I pre-multiply by what? By R transpose, which is the same as R inverse. Correct? I told you that here. Depending on which direction you are going, correct? You do the inverse, right? Or the transpose of that. So that's the case here. That's like this one. I have it in frame 0. I want to go back in frame 1. So I need to multiply it by the transpose of this, which is this guy. And that's what I do here. As you can see, this guy here is that rotation matrix. This one. I transposed it and then multiplied by the result I found from the previous step. And when you do that, guess what you would get? You would exactly get the result. So here there is one thing missing. Let me add that. There is one thing missing here. It should be this one times this is equal to that. Okay, so I wrote the final result here. So as I said, I multiplied the transpose of that rotation matrix by what I found, and I got what? My final result, which, as you can see, if you look at it, it is exactly the same as what you can get from those geometric projections. Okay, so it's your first application here. This process might look a little bit more complicated than just doing all these projections, but the matter of fact is not always everything is that small projecting it, and plus it's a systematic process here. Once you know your rotation matrix and once you know how to add stuff from the same frame together, that makes life very easy. Okay, so it's just a matter of one thing, my last word. I'm adding vector A to vector B and I want to get vector C. Or let's say I'm multiplying vector A by vector B and I want to get vector D, right? These are vectors. The only important thing is this. You are writing these vectors along the axis of which frame, right? Every vector is determined when you decompose it along axis of some frame. If I'm writing this about frame 1 or on the frame 1 axis, this also has to be on the same frame, and the result is also going to be along the axis of that frame. If here I decide to write B on the axis of frame 0, then also A has to be on frame 0, and the result is going to be on frame 0. I can never do something like this, where this is frame 1, this is frame 0, and this is frame whatever. Okay, this is not workable. Okay, you can only add stuff that are written in the same frame. So as long as I follow this simple principle and I know how to go from one frame to the other by using a proper product of a rotation matrix, everything else in this course is not going to be that difficult. It just needs practice, and we are going to do tons of practice in class. But here, I just wanted you to know about the basics of rotation matrices, how they are defined, what are the properties, how we can transform a vector, a matrix, and everything with them, how we can combine them, give you some examples, and hopefully this long video will be useful to you. Okay, I actually remember that I needed to show you a little bit of how to use MATLAB symbolic toolbox for performing some of these linear algebra here, and I forgot, but that's not really a hard thing. All you need is the command sims, define something symbolic and let MATLAB take care. But here I'm going to show you a little bit of that, so that's okay. So let's say, for example, I want to calculate this rotation matrix, right? And if you remember, I showed you that the rotation matrix is something like this, correct? So you can sit down and do all the multiplications and try to use your trig knowledge and simplify it, which is a very good practice, but you can also use MATLAB to help you. So here, if you can see, I have defined my angles and angular velocities, theta, phi, psi, and then theta dot, phi dot, psi dot, all of them as symbolic variables, okay, sims. And then here I'm defining those three rotation matrices. This is my first rotation matrix, rotation z and psi. The next one is rotation x and theta, and the next one is rotation again z and phi. And here, this is A times B times C, correct? That's the rotation matrix. So what I do here is I define these rotation matrices, and I always recommend when you write these, do not shut down the output. Make sure you see the output just in case here you made a mistake in entering one of these zeros and ones and your form of the rotation matrix is wrong. So I always recommend make sure you visualize them before you're multiplying anything. Okay, so here, if you go and look, these are my A, B, and C matrices. You clearly see that's a rotation of Z and, X and theta. B. A is a rotation of psi and Z, and this is a rotation of phi and Z. So first make sure it is extremely accurate, because a small lack of accuracy, smallest typo will lead to completely different result. And now I multiply them together and I will get what? My rotation matrix. And if you look at the elements here, you see the element 3, 3 is cosine theta. This element is cosine phi sine theta. Well, the element 3, 2 is cosine phi sine theta. This one is sine phi sine theta, correct? So sine and cosine phi times sine theta and then cosine theta. And if you look here, you exactly see that. Cosine theta, and then what? Sine theta times sine phi and cosine phi, which you can clearly see here. Sine phi and cosine phi. Or this element here is cosine phi, cosine psi, correct? Cosine phi, cosine psi. Look at it. Cosine phi, cosine psi minus sine psi, cosine theta, sine phi. And that is this one here, negative cosine theta, sine phi, sine psi. So if you just write these with that simple abbreviation that for sine you show S and for cosine you show C, that is exactly the result. So MATLAB did all of the arithmetic for us and gave us the nice form here, which we can make sure that our calculations are correct. The other thing is, let's say here, for example, I wanted to add these vectors together. So I first formed my psi dot vector along Z, multiplied it by this matrix A, the first matrix, and times the theta dot 0, 0, and then added the product of the two first matrices times 0, 0, phi dot to get my omega of 1 with respect to 0 written in 0. So this is what you can see here, right? A times theta dot, A times B times phi dot, and then psi dot, added them all together. So this omega is that omega 1, 0, 0. Okay, and if you want here, let me show you the result of that. So that's all it is. I multiply it and then I get my result. If you look at the last element, it's psi dot plus phi dot cosine theta. That's what you see here, psi dot plus phi dot cosine theta. So you get these three elements here, as you can clearly see. And then what I do, I multiply it by the transpose of ABC. And that's what I said, right? Multiply ABC to get the rotation matrix, transpose it to get you back from frame 0 to 1, and multiply the transpose of the whole thing by the result in the previous step, and that should get you what? Exactly what we made in those, what we showed in those, in that dynamic video using geometric projections and formulas. And here, that's what I do here. And it gives me this result, which quite is long. Okay, so this result does not look as nice as that guy that I have over here. Okay, it's quite more terms in each one. But it doesn't mean that MATLAB did it wrong. It just didn't simplify the results. Here, there are a bunch of sine squared and cosine squared terms that you can add to one, or there are some positive negative terms that can cancel out. So if you see something big like this, let MATLAB try to simplify it and simply say simplify, and then whatever variable that you are trying to simplify. Just say simplify this for me, see if it can do it. And if you do, there we go. Now it made that whole big thing that you had up there into this nice form. Phi dot plus psi dot cosine theta, which you can see here. And then the top two terms, theta dot cosine phi, correct, which you can see here, plus psi dot sine phi sine theta, which you can see here, and then the next term. Okay, so once you know how to work with MATLAB symbolic, and all again you need to do is to use the command sims, and sometimes the command simplify. Define your matrices. The transpose operator works fine. I recommend when you are dealing with matrices like A, B, C, or omega matrices like A or so, you can use a transpose, but it's not going to give you anything nice. Okay, so if you want to transpose a matrix when it is all symbolic, do not use the quotation mark for the transpose. Okay, it is going to give you this conjugate, and it is going to go on your nerve really. And what is this? I recommend whenever you want to transpose a matrix that is symbolic, use the command transpose instead. For a regular vector with numbers, they both do the same thing. For symbolic, the command transpose is acting better. Okay, it doesn't bring this conjugate and stuff. So that's why you see here, I use the command transpose and I did not use the command, the quotation mark here for transpose. Okay, but that's basically all it is if you want to do it all symbolic. Now later, when we go and I show you the other ways of representing rotations, like Euler angle, axis angle, quaternion, there are lots of commands in MATLAB robotics toolbox, which can take one form of the rotation and give you the other form of rotation, and I'm going to show you, but these are for future videos, okay? Thank you so much for your attention, and I will see you in the next lecture. Thank you.